Right. So as we said earlier, there are some limitations to this treatment of plasma frequency. Nonetheless, it's a very useful, very instructive one in practice, and let's go to one such illustration. What you see here is emission, radio emission from the solar corona. I chose this example because it's kind of my field, and B, this is one of the few direct examples of the application of plasma frequency in astrophysics, at least near Earth astrophysics. Now, this diagram will take some explaining, and so let's do that. What this is you've got this is a whole. Okay, let me bring this up. So this is what you call the sun as a star. This is jargon observation. In other words, you simply point a radio antenna at the sun, and okay, and so that's my sketch of an antenna, and you do not or rather, this does not image the sun, the sun's surface, or we'll just call it the sun. Okay, it just captures. In other words, you cannot make out, well, this emission is coming from here or here or here. No, you cannot. You just know that the emission is coming from this direction. And from the fact that your antenna has every antenna has a certain beam width, like that. It has a certain beam width. Okay, this is essentially the gain. This is the pattern in which the gain of the antenna is maximum, and you pointed it at the sun. Okay, and the sun being the most powerful object, radio object, and it's simply because it's so nearby. Okay, and hoping that some of these emissions are not coming from terrestrial other antennas that are located nearby, you know that everything that's being recorded by your antenna is simply coming from the sun. That's all. So you don't know where it's coming from on the sun's surface. That's what we mean by kind of a sun as a star observation. It does not image the sun. Okay, and what you've got here is time on the x-axis and frequency on the y-axis. So you're sweeping. So this goes from about 50 megahertz to about 2,000 megahertz. Okay, technically it's 25 to 2500 megahertz, and this is from an observatory in Japan. It's called Hiraiso. We have a similar setup right here at ICER, and it's continuously obtaining these kinds of data, and we have a small antenna up on the roof, and the receiving apparatus is in the storeroom that's right next to my office. So if some of you are interested, maybe one of these days, when you're all back on campus in those happy circumstances, we can take a look. Okay, so going on, what this is. So right. So what this instrument is doing is it's sweeping through frequencies from say 25 to 25,000 megahertz. Okay. And so it's sweeping very fast. If some of you know something about the old electron gun kind of TV screen, that's what it does. TV screen sort of rasters across. It rasters across the screen. That's sort of what this is doing in frequency. Okay, and so but the sweeping frequency is of course fast enough such that this kind of a thing makes sense. Okay. So, so looking at this, and the color scale is such that deep yellow. I'll come to the point. Okay, you must be wondering by now what all of this has to do with plasma frequency. I'm describing the observation first to make it clear to you, and then we will come to where plasma frequency fits into this whole picture. So, so this would be brightest emission. Okay, and somewhere here, this is the color scale. Somewhere here, somewhere where it's blue, would be faintest. Okay, and this red is somewhere in between. So, what this is telling us is that there is bright emission originating between. So this is time in universal time. You can roughly think of it as Greenwich Mean Time, right? So on this particular day, 26th of October 1993, way before many of you were born, I think. From 0030, say this would be 0045, so this between here and here is 10 minutes, and so you can read off the time from here. And so roughly starting from here up until here, you've got something in the solar corona. Okay, and why do we know that it's a solar corona? We will come to that. Okay, it has to do with the fact that the plasma frequency is proportional to the square root of the electron density. Okay, now you've got a bright band of emission drifting fairly fast from about 200 megahertz down to about 50 megahertz within a span of this many minutes. This is one observation you can make. The other observation you can make is you've got a bright band of emission drifting from, about, what would you say this is, about 150 megahertz to about 50 megahertz, right? Over a much larger time scale. It's drifting much slowly. Okay, so this would be, relatively speaking, slowly drifting emission, and this would be relatively fast drift. And notice we are essentially paying attention only to the brightest parts of the emission. Okay, so now what we are really saying here is that, remember, now we'll come to the interpretation. Remember that the plasma frequency is proportional to the square root of the density. Okay, and if that was a sun's surface, any hydrostatic, any surface in hydrostatic equilibrium, turns out that the corona is not really in hydrostatic equilibrium, but nonetheless, if this is a surface, by surface I simply mean, I put that in quotes, the photosphere, suppose, and this is the extended atmosphere above it. So you would, as you climb in height, you would have decreasing density. Okay, so decreasing density with increasing height. in the solar atmosphere. Okay. Now, if you make the one-to-one correspondence that the omega PE is observed frequency. In other words, the frequency that you're observing, the frequency emission that you're observing, if you're observing emission, say at 200 megahertz, say somewhere here, okay, this is actually plasma frequency. That's the assumption that we're making. This is actually plasma frequency. So this emission is this radio emission is being emanated at the plasma frequency corresponding to that particular layer. What do you mean by that particular layer? The layer that possesses a particular density, okay, a density such that its plasma frequency corresponds to 200 megahertz. So as time progresses, the plasma frequency is decreasing. In other words, whatever is exciting this emission is moving upwards through the atmosphere. Okay, so this is decreasing frequency, increasing height in the atmosphere because of this. You see, as you go up from the surface, any atmosphere, decreases in density. So you have, you come down, the plasma frequency increases. You go up, the plasma frequency decreases. Okay, this is pointing to this has all the telltale signs of pointing to an exciter. Whatever is causing this emission is drifting at this particular speed. If you map the density to a model of the solar atmosphere, you can map the density to distance. Okay, and the frequency can be mapped to the density can be mapped to the distance. So indirectly, this y-axis can be mapped to distance or height in the solar corona, and the x-axis is time anyway. So from this, from a delta y over delta x or dy over dx, you can get an estimate of the speed at which this exciter is drifting. Turns out that these represent beams, fast drifting structures such as this. Frequency versus time, fast drifting structures such as this represent electron beams almost near relativistic electron beams traveling through the corona. And what are they doing? As the electron beams travel through corona, they excite instabilities, and they excite density oscillations, because that's what the plasma the plasma frequency is. Plasma oscillations are density oscillations, not electromagnetic waves that you're observing. But okay, so they are not electromagnetic waves. But then there is, a lot more that I haven't told you. It turns out that through a three-wave mixing process, there is a momentum matching condition, just like this kind of three-way mixing process. This would be, for instance, the K1 or omega 1 plus omega 2 equals omega goes to omega 3. So you have to presuppose the existence of another population of waves which will mix with the so you also need you need to satisfy these two simultaneously. okay, such that the omega-3 is nearly equal to omega-1. This would be the observed electromagnetic emission, and this would be the plasma oscillations. There needs to be an additional source of low-frequency waves, and it's, the existence of such a population is not implausible. As with everything in astrophysics, it's all about plausibility arguments, and so you need this kind of a mixing condition plus a k, a wave vector mixing condition. Both of these have to be simultaneously satisfied. All I want to say, I don't want to overburden you with the details. All I want to say at this point is that do not, although we are pretending as though these are plasma oscillations, it just happens that the observed electromagnetic radiation is at the same frequency as the plasma oscillations. That's all. Observe electromagnetic radiation, these are transverse electromagnetic waves. These are by no means density oscillations, which is what plasma oscillations are. It just happens to be at the same frequency in this particular instance. And these are signatures of electrons that are traveling rapidly. So like I said, you can calculate the speed, and the speeds turn out to be quasi-relativistic, almost relativistic. This, on the other hand, is a much more slowly drifting feature. This kind of emission is most likely due to the passage of a shock through the solar corona, which is exciting electrons near it. As the shock passes, it's exciting electrons near it. And the excited electrons are, in turn, exciting plasma oscillations, which then undergo these kinds of three-way mixing processes and ultimately emit electromagnetic radiation. Okay, so this was an example of radio emission in the solar corona, a solar wind. The distinction is a little unclear. The solar wind essentially emanates from the upper part of the corona, so therefore, okay, right. The other thing is a shortwave radio communication. I don't know how many of you are aware of this, how many of you have ever listened to shortwave radio. In the early days, these were the only kinds of, before FM became popular, shortwave communication was the only thing available, and even today military communications and many other kinds of communications rely on shortwave signals. Okay, again, it's just a matter of look up Google shortwave. Okay, that'll give you a range of frequencies. Now, what has it got to do with this this cartoon? What this is you've got a transmitter, a shortwave transmitter, and a receiver situated far apart on the Earth, so far apart that the curvature is apparent. And this would be a layer in the ionosphere where this is electromagnetic waves. Okay, these are EM waves traveling through the atmosphere, and here the plasma frequency of this layer matches the frequency of these waves. Okay, so the thing is, when these electromagnetic waves hit a particular layer in the ionosphere, okay, now as we said, the omega PE is proportional to NE raised to 1/2. So by saying the plasma frequency of this layer is this much, we're essentially saying the density of this layer is this much. As you go up in the atmosphere, the density decreases, and the plasma frequency also decreases. All right. So, but at this particular layer, the characteristic of this particular layer is that the plasma frequency matches the frequency of these electromagnetic waves, and this causes the wave to get reflected. Why is that? Well, the electromagnetic wave has electric fields, right? And the electric fields are what happens is the electric fields are shorted, so to speak, by plasma oscillations. How do you understand this? One way of understanding is, what does the electric field do? It pushes electrons around, right? You have an electron, and in the presence of an electric field, it feels a force. So E pushes electrons. Okay, now, but you see, I mean, you know, a plasma is a lot of, whole lot of mobile electrons, very, very mobile electrons, right? So if an electric field tries to push an electron this way, a whole bunch of these mobile electrons will immediately rush in and neutralize or short, in electrical engineering language, the E field. Okay, the E field, what it does is it tries to displace the electrons. Okay, but owing to the presence of the plasma, and this displacement is quickly annulled and of course the E field is oscillating, and the oscillation frequency is exactly the same as the plasma frequency, okay, or very close to the plasma frequency at any rate, and so there is immediate shorting, okay, and so the E field goes to zero exactly at this layer, and that's exactly the condition for reflection, right? When the E field goes to zero, this and this exactly cancel each other, and so the E field goes to zero here, and that's exactly the condition for reflection. So the electromagnetic waves will get reflected at precisely this layer in the atmosphere where the plasma frequency matches the electromagnetic wave frequency, and the short wave frequency at which the waves are being transmitted. And so short wave communication relies on this concept of plasma frequency. Okay, and so and the geometry has to be very precise. Okay, if for some reason due to a geomagnetic storm or something, the height of this layer alters, if it moves up or down, then this entire geometry is lost. Okay, this is the origin of shortwave fading and many other complicated phenomena. Okay, so I just wanted to alert you to this. We return to this figure that we had seen earlier. Plasma states in the universe. This is a temperature versus density kind of diagram. So these would be low temperature plasmas, high temperature plasmas, low density, high density plasmas. Why am I showing you this? Because the numbers are very, very important in physics, and the next here are some typical numbers. Okay, in the interstellar medium, for instance, these are the kinds of number densities, these are the kinds of temperatures, these are the typical magnetic fields, and these are the typical plasma frequencies, Debye lengths, number of particles per Debye length. So you see here the number of particles in a Debye sphere is decent. Okay, you could call this a good plasma. Okay, by the time you come to arc discharge, there are only about 40 electrons in a Debye sphere. You're treading on thin ice. Okay, by calling this a plasma, and so on and so forth. Whereas a tokamak plasma is even better, much better. Okay, the number of particles in a Debye sphere is much larger, and all of this this simply comes from all of these numbers. Okay, so you don't have to use the magnetic field, of course. As of now, we have made no reference whatsoever to magnetic fields. We will come to that as we go along. And right, yeah. So this is where these would be gyration frequencies. You already know about this, even though we haven't used it. You know the charged particles gyrate in the presence of magnetic fields, and so these are the gyration frequencies. So and this would be inertial confinement field. The very same things. The very same different kinds of plasmas that we looked in this diagram. So these are the typical numbers for that. And right. So that pretty much completes our module 1A, and we will take up other issues when we meet next.